Okay, so hello and welcome. Howdy, here we are. Maximum gap, hard, part 2, C++, LeetCode. Let's go. So yeah, brother, I spent 2 hours on this question trying to figure out what was going on here, and I have to admit, I did end up taking a look at the discussion because I thought about it some more, and I was like, this is actually impossible. So it's not impossible, but it's like quote unquote impossible. Here's what I mean. Let's just say it's very important. The note that the numbers are between 0 and 10 to the ninth. And I kind of forgot about this algorithm, I'll admit, but there is an algorithm that you can use to do this. It works. It's quote unquote works. So let's start with the proof that this is actually impossible if you don't use what I'm going to describe. So the sorting bound under sort of normal conditions, there's at least two computational models. One computational model, if you use comparison sorts, there's an n-log-n bound on comparison sort, so you cannot use comparison sorting to achieve a lower bound if the solution requires sorting. Now, the way you can prove that the solution requires sorting is this. Actually, the solution, you can prove that. But if it requires comparison sorting, then you can't do better than n-log-n. And that's very important because we're not going to use comparison sorting. You can prove that this requires sorting, but you're not going to use comparison sorting, and that kind of gives away the answer. So linear sorting there's like a few different types, but there's bucket sort, counting sort, and then there's like kind of a lot of different algorithms out there. But you can kind of consider them as like meta algorithms. Bucket sort, really, they're all different types of bucket sorts or distribution sorts, and they're like more like a meta sort. They basically break up the your set of numbers into buckets, and then you can either employ another sorting algorithm to sort the buckets themselves, what's inside the buckets, sort what's in the buckets, or you can employ a sorting algorithm to sort you have to employ some kind of sorting algorithm to actually sort the buckets themselves, or so not what's in the buckets, but the buckets. Like if you kind of gave them a label and you wanted to sort them and put them in the right spot. Yeah, there's different ways to do that, sort the buckets themselves. There's different ways you could use your bucket sort to sort the buckets themselves and recursively one direction recursively sort the buckets, and then also recursively sort what's in the buckets, but using bucket sort again. Or you can employ some other sorting algorithm on the buckets or what's in the buckets, as you wish. Radix Sort, the one we're going to use, is basically going to use counting sort, and what I'm going to use is counting sort, and we're going to use sorting the buckets themselves using counting sort, and then each bucket we're going to sort again. We're going to try to do this inline and use what's called Radix Sort, which goes like a digit by digit. I'll explain what that does in a moment. Yeah, so you could prove that without using if you used the problems are with sorting becomes a little more complicated. So comparison sorts, as I said, it's n-log-n is the lower bound. It would be impossible to get the linear bound here if we use comparison sorts. You can actually prove that you need to use sorting for this algorithm, and the way you'd prove that is you would say that in order to compute the maximum of these numbers that they're looking for, that's whatever set of numbers you're dealing with. In order to calculate the maximum of a set of numbers, you need to know every number in that set. You need to visit every number, or you need to find a way to not have to consider either have to visit every number or somehow know something about those numbers such that you don't need to visit every number in order to know what is the maximum. But if there's just like random numbers, then there's no relationship between them. They're independent variables, more or less. Then you're out of luck. You're going to have to visit every number. What that means, though, is that in this case, this difference of successive elements, in order to know what the difference is, you need to know what the two other elements are. there's no way to know what the difference is without knowing what the two elements are that generate that difference. I think you probably could prove that. I don't really have a proof of that immediately. And then if you do know the two numbers and what their differences are, and that they're the closest successive elements, then what you can do is you take all of those differences, take the smallest element, and then or take the largest element or the smallest element, however you want to do it, and you could generate the sorted list. So you can then, if you had enough information to compute this number, you could generate a sorted list. That's the point. And that proves that you need to sort this, sort these numbers first. So you need to use, but if you want to use linear time sorting algorithms, you can't use comparison sorts. You have to use something else. So I caved in and looked at the discussion. They mentioned Radix Sort, and I was like, oh, okay. All right. Yeah, unfortunately, I tried to use counting sort and or pigeonhole sort because I realized like, oh, that might work here. But the numbers are a little bit too large in the range for me to reasonably use counting sort or pigeonhole sort, which basically would go through like the whole range of a possible number, like literally the largest number possible. You would take with, I think, pigeonhole sort, you would generate the entire range of number. I think counting sort and pigeonhole sort are similar, where you generate the entire range of in memory of all of the numbers you could possibly have, which is really excessive in terms of the amount of memory you need. Radix sort is a little bit better. You need like a more like a logarithmic amount of memory with respect to this number. Yeah, it's a lot more efficient. So that's what we're going to use. And in this case, it comes out to be, relatively speaking, constant because there's only at most 10 digits per number. And so yeah, you only have 10 extra steps per iteration. So it'd be sort of like O of 10 times n, which is just O of n. So that's a linear amount of time, and the amount of space we need is, I think we could do this in place if we wanted to. I'm not going to do this in place, but yeah, the online, it said worst case is O of n plus w, where w is the word length, where a word is like the number of digits or the number of, you could also use strings too. You can use Radix sort on strings. Anything that has a lexicographical order, you can use Radix sort, which is pretty efficient. It's effectively linear time. Comparison sorts work too, but Radix sorts is nice as well. Anyway, so yeah, that's what we're gonna do. Like, it's actually a pretty easy question, easy problem overall. It kind of got derailed for hours on end because I was just like, I spent a lot of time thinking about this. It's like, I don't think it's possible. I basically was trying to formulate a way to prove that's impossible, and I pretty much did. Because the difference, like, you could reformulate these differences as like just knowing what the two successive elements are. That's really, you have to know what those are in order to know what the difference between those two is. And that's kind of it. Yeah, that's what it comes down to. So anyway, we're gonna go ahead and you actually, even if you didn't know what the successive elements were, you could just take all of your differences and put them into a set and put all your numbers into a set, check your differences against the smallest number. Actually, that would give you can get back your sorted set, but that might be too inefficient to do that. But you still could use it, even if you didn't know, you still could generate the sorted set from this information. You couldn't do it efficiently. Trying to think. Does that matter if it's efficient or not? It might. You don't immediately get the sorted list, but you could still, even without knowing what the two successive elements are that generate that particular difference, I think you could still at least get your generated set, your sorted set. Anyway, I think the problem is that if you Yeah, if you could generate the sorted list in a time better than n log n, then you've run into a contradiction. That's the problem. Which certainly, if you knew the successive elements, you could. And then I think we'd have to prove is that you wouldn't be able to know what the differences are without knowing the successive elements. I mean, how do you know what the difference between two numbers are without knowing the numbers themselves? I mean, you could just be told that, like in other words, you could just be not given that information. But if this is computed from something, I mean, it has to be from those elements. And so I think you do need to know what those elements are. I'm trying to think if there's a way to easily go from just the differences back to the sorted list. Huh. Let me think about that for a minute. Can you do that? I know you can certainly do that if you only know one of the numbers. If you don't know both of them, but you know one of them, that's enough. Like I said, I don't know how you can. I don't know how you can even compute that without also computing that information. That's kind of my argument. Maybe it's not like a solid proof, not really a rigorous proof, solid proof, but it's probably the case that it'd be impossible to determine what the difference between two successive elements, what all those numbers are, without knowing at least, without knowing both, without both knowing one of the numbers and and really knowing, figuring out what both of those numbers are at the same time simultaneously. I don't think you could. Anyway, all right, we're spending a lot of time just kind of chatting here. Let's go ahead and try to code this. So this is going to be Radix Sort. What Radix Sort is the way we're gonna do it. We're gonna have digits 0 through 9, which is 10 digits. So we'll have 10 buckets. We're going to place all of the n number. We're going to create a new list of numbers. I want to try to do this in place if I can. I don't know if I can though. All the numbers 0 are going to come first, then all the numbers 1 are going to come next, and so on. We're going to rewrite into the array. And this is going to be, in theory, a stable sort. So we could swap. That's what we could do. We could swap all of the. So we could set up pointers or indices into where the beginnings of each of these are into the array. And we can push. Can we do it that way? It's actually. It might be better just to count how many there are and then swap the elements as needed. Yeah, it's probably better. Yeah, first count them, second swap them. That can give us a stable sort, and then we're only going to require 10. So actually, this could be linear time and constant extra space. We do this in place of the stable sort. We're going to copy the array though. We're going to do it that way. Yeah. So okay, so let's do that. So we'll just say int array ns.size for int I equals 0. Oh yeah, it's less than n. No. I. And what we're going to do is take array of I is going to be equal to ns of I. And so now we've copied our numbers. And now what we're going to do is we're going to create, so here's the description of the algorithm. Create 10 buckets, count for, we can do for each digit, and we actually want, oh, that's interesting. So this is kind of interesting. So I want the most significant digits to be at the bottom. The tricky thing there is some of these, there's a few things that are tricky. I wonder if we could sort by, I wonder if we can, I wonder if we can sort by, could definitely use like modular arithmetic here to get the, how do we do this? The things that end with 0 don't necessarily need to go at the top. I'm just thinking, how can we do this? I think it's the most significant digits you want to go left to right. Because if you sort by the least significant digits, they don't carry from right to left. In other words, like if you put something that has a 9 at the bottom, that could be just the number 9, and there could be like a billion and that ends with 0, and that 0 is going to end up above 9. So you actually have to go left to right, I think. The tricky part about that is you need to, for the things that don't have the digit that you're looking for, I guess one question is, do I want to replace all these numbers with an array of digits first? I don't really want to do that. That seems kind of excessive. We can do, like as I said, like a kind of modular arithmetic, but it's kind of unnecessary to do that. Not a modular, just a division. Yeah, just a division by 10 raised to some power. Problem with that though is that that number. Yeah, I mean we could do it that way. That's fine. That's fine. It works. It's just a division each time. Yeah. Okay. Also, all the zeros will just go in the top bucket or the first bucket. Yeah. Yeah. Okay, that's fine. That works. Division is fine. Okay. Div is just going to be standard power of 10 raised to the 9th. So we'll start with a billion. We're going to say 4. Actually, we could. Now we're going to say div is greater than or equal to 1. Div divide equals 10. So we're going to do this for each digit, more or less, each divisor. And we're going to say for each int I equals 0, I is less than n, plus plus I, const int x equals array of I. So first we want the counts, employee counting sort. Radix sorts intermediary. My Radix sorts intermediary sort. Radix sort intermediary sort. Or the intermediary sort of my Radix sort. Yeah, so employee counting sort. The way we're going to do that is, so here I am saying this is such an easy question, and here we are 20 minutes later, still figuring this out. So the way we're going to do this, I think, is to count. So we're going to say int count of 10, and that's going to start off at 0. So we initialize that to 0, and we say if x divide by div, actually we're going to say const int which, there's w or d, you could say. All right, integer division, and we're going to increment count of x of d plus plus. Right. So, and then we're going to say similar thing here. So now we can say what we want to do is we want to swap all of the numbers that we see into each bucket, and we know what the sizes of each bucket are, and we know where the indices of each bucket begin. Yeah, so we could do something like we could have initial pointers or positions. So we could just say like int position of 10, and we could say for I equals 0, I is less than 10, plus plus I. So we'll say position of 0 is 0. Yeah, I mean, there's current equals current, and then current plus equals count of I. Right, so the initial position for things with 0 digits will start off at 0. Then the initial position for things with 1 digit will start off at, add all that index over, or move that over. We could do it that way. That should work. That's fine. And so now we can say for int I equals 0, I is less than n, increment I, and now we actually perform the moving. So we're going to say same deal here again. So we do one pass to get a rough idea of where we should place the elements, and then we'll do another pass to say we're going to say if, so D, it's going to be standard swap array of I with position of I, and we're going to increment by 1, position of D plus plus. So yeah, so it looks like this now. So we get our value, which is X, we get D, and what we're going to do, and it's actually this array, this position is going to be array of this position. Array of position of D incremented. So that's a little confusing, but what it means is whatever this number is that we're looking at, we're going to swap it with, oh, but this is kind of a problem, isn't it? Because, oh, that's awkward. Yeah, counting sort's a little bit easier if you just copy a new array and then copy it backwards. Yeah, it's a little bit easier to do it that way, but the problem with this is that the number that we're swapping it to is not necessarily in the correct spot. No, wait, this is okay. Yeah, so so the number that we're looking at, we're going to move it to another position. And the number that we just moved to this spot, that might not be in the right spot. So actually we need a while loop to make sure that all the numbers are in the right spot. So we can say while, so I'll start with this. While, how do I make sure it's in the correct spot? Yeah, you would take the two indices. So there's position of D, and then there's position of D plus 1. And you want to say this current position I, it's less than or equal to, it's so confusing. I is got to be greater than or equal to D, and I is got to be less than D plus 1. Wow, that's not the case. While this is not true, we're going to swap and recalculate. So these are not going to be constant anymore. This would still be in place, but it won't be, and it'll still be linear. It's still O of n, but you get one extra. You get like at most 2 passes, right? Because what can happen is that basically every number ends up swapping through the first element, and then you just check all the other elements are in the right spots. So this is an interesting way of doing this, but yeah, we want to do this. We're trying to do this in place. And again, we can operate directly on NS instead of on array of n, but I want to work on array of n. So now, how are we doing? 20, almost 30 minutes. So there is a problem here. If D is 10, we need to make sure while I is not in the right position, which means it's greater than or equal to this spot, but less than this other spot. And this is end. This would be basically if D is greater than 9, something like this. You just have to add this extra guard here so we don't go off the edge. So if D is 10, so D is 0 through 9. If D is greater than or equal to 9, then this will just automatically be true, this part. So we only have to make sure that this is the case. If it's less than 9, then we have to check the second part. So yeah, that's a tricky thing, but that's just to make sure we don't have an what do they call that, a like out of bounds exception type of thing, array exception, out of array bounds exception. Okay, so yeah, so if this is not the case, if I is not in the right spot, so to speak, then so I is to the right, but it's also less than the other one, the one that's ahead of it. It's not in the right spot, then we're going to swap I with where it should be, and then we're going to recalculate I. Recalculate this value. So after we've swapped, now we're looking at whatever was there, and we've updated X and D. Yeah. So that'll do our swapping repeatedly until we're in the right spots. This will give us an in-place kind of a maneuvering, and is there anything else we need to do? Or don't we just do that for each? Let me think here. Now, yeah, I think this is right. Part of the problem here, so one question here would be, let's say everything had digits 1 through had digits in every. Let's say all the numbers had the same number of digits, right? So let's say it's 6 digits. We move all 0 through 9. So 0 is in the beginning, 9's at the end, or 1 through 9. 1's the beginning, 9's at the end. When we look at the next digit, might have a problem, because let's say we have a 1 9 and a 9 1. Well, the 9 1 is going to go all the way to the top, whereas the 1 9 is going to go all the way to the bottom, which might not be correct. Maybe we are supposed to go right to left, actually, because the more significant digits have a higher precedence than the less significant digits. That could be the case. Yeah, what I was thinking was that each bucket itself could be sorted internally, but I don't think we need to do that. Because this is somewhat stable, we could sort the things on the right side, sort the least significant digit first, and then more significant digits would change those positions, but the positions relative to the least significant bit digits for the ones that don't change wouldn't change. Yeah, that's confusing, but yeah, I think it's right to left we want to do. That's actually very confusing. So we'll start with 1, and then less than or equal to. We can use a count instead too. We could just say like total We'll just say 9. So div multiply equals 10 and total decrement. I don't actually know what's going to happen here. If we go 9 down to 0, 1 through 9 is 9 times. So we're going to go 1, 10, 100, 1,000, 10,000, 100,000, a million, 10 million, 100 million, a billion. Yeah, 10 digits. Okay, that's correct. That's correct. So, is that right? It really should be 10 times. All right, because when you multiply, that's confusing, but yeah, it's actually 10 digits. And we're actually going to start right to left, and then so we'll sort array of n, and then we can process the differences, retrieve the maximum successive difference. And the sorted array. Oops. So we'll have int ret equals 0, previous equals -1, I equals 0, I is less than. You can actually do, this is maybe easier. Yeah, okay. So we'll say ret equals standard max of ret and previous of I minus previous I minus 1. Something like this. This, by the way, we could probably put in a one of the algorithm, what do they call that? One of the algorithm, STL algorithm routines. Oh, there's array of I, the previous of I. It's probably some kind of calculation we could perform here. Not calculation, but some kind of a, yeah, what was I saying? This could probably be a cumulative function, something like that. Actually, maybe we'll want to rewrite this as a cumulate function, as a cumulative. The only issue is that this array is actually not a, like, I don't know if you can use standard begin, standard end with this. Maybe you can. I'll try it in a moment. But out of bounds. Oh no. Uh-oh. Index 6 out of bounds for, position of D plus plus. Sort of a 0, can count I. Oh, why did I do this twice? Oh, I think I was gonna modify the second one. I don't. What? I don't. Okay. How did that happen? Runtime error. Okay. Dynamic stack buffer overflow. No kidding. Wow. Oh, that's why. Oh no. No, position I gets set to current. Yeah, we actually do initialize position correctly here. Well, that's awkward. Huh. How are we doing on time? 40 minutes. All right. Not too bad given how long I had thought about this question before trying to solve it. Where's the runtime error occurring? That's the question. Okay. Yeah, let's try this. Let's see where this is happening. Let's see where this is happening. Check 10 immediately. So after the first division, by the way, there is a problem with this division that we're doing here. We actually want the this is really subtle. This is tricky. We actually want the rightmost digit. The division that we calculate, we actually end up with oh, that's probably why the runtime error is happening. When you just divide, yeah, you lose the rightmost digits, but the leftmost digits are all there. So, like if you do 100 million divided by 100, you still have a million. You want the rightmost digit of that. So actually, you would take so you take the divider, and you take that modulo 10. That's super subtle. It's extremely subtle. Not subtle, but like it's kind of something you don't want to mistake that or miss that. And that way you won't get the digits that you're supposed to be getting if you don't do this properly. Okay, still get a runtime error. Why? What is the error? Where is this happening, this error? Do we get to at least the second one? Alright, we get to the second one. Do we get further than that? Let's make this the fourth and the third one here. Okay. Alright, how about this? How about this? 20, 10, 20, 30. So this is where the problem occurs. Okay. And why would that be? Let's go with put a 35 somewhere in here. Okay. Alrighty. So 35, 35. And then I guess we get a bunch of routines inside here. Let's make that 36. So this is the code that we have issues with. 1, 2, 3, 35, 1, 2. So 35, and we get swaps galore. Excuse me. All kinds of swapping occurs. Now my question is, maybe we're not calculating this correctly. X divided by the divisor in modulo 10. If it's divided by 1, we take modulo 10, and we should get the rightmost digit. If we divide by 100, we divide by 10 in integer division, then we take modulo 10, then we get the second rightmost digit, and so on. But my question would be, like, how do we buffer overflow? How does that happen? 35, 36, 36. Oh, excuse me. That's why. Duh. Well, yeah. If you're 9, and you say this is true, then you won't look here at 10. Okay, which line exactly is causing the error? I want to figure that out now, because I don't see it. 37. So the last thing that was called was 36. So it could be 37, do 38, and 39. Okay, let's try that. 36, 37, 38, 39. Let's try these things. 36. So there was a 39. So 30. So we didn't get to 37. So somehow here, this position went off the side. I think that's the issue. This position D was too big. How did that happen? Maybe my formulation here is just wrong. Like maybe that's the issue. Maybe I just don't have this right. That could be it. That could be it. Position D is 4. 0, 1, 2, 3. Yeah, that's the problem. It's way off the edge. What is D and what is X? Because that shouldn't have happened, I think. Or we would not expect this. And also, what is div and total? I think they're all 1. Okay. Okay. So X is 9, D is 9. That's correct. Div is 1. Total is 10. Oh. Yeah, that's the first division. So we got 9. How do we get? How many of these were at 9? There's only one of these. Position of D. Huh. How did position of 9 end up at 4? What? Huh? What is going on? these are the prefix sums. Are we not calculating these correctly? I think we are. I am so confused. How do we get 4 here? How it happened? 0, 1, 1, 2, 2, 2, 2, 2, 3, 3, 3, 4. Whoa! What? How do we get 4? Huh? What? Hmm. Huh. So confused. I did my math wrong on this. So the first section is 0. Sorry, I'm just so confusing. The first section starts at 0 and ends at the position of the starting point of the next. Yeah. And the starting point of the next is going to be equal to the sum of the total of the first section. Yeah, that's fine. The next section, you would add to that starting point however many are going to be there. So let's say there's one element there. You would get an ending position of 2 and a starting position of 1. You would not go past 2. And if there was another element, it would be starting at 2, ending at 3, and finally another element would be starting at 3, ending at 4. So 0, 1, 1, 2, 2, 3, 3, 4. So how did we end up with 4 from 0? How did 0 go all the way to 4? 0, 1, 2, 3, 4. 1, 2, 1, 2. So there were 4 elements. So we added 1 4 times. Oh, that's so confusing. What? Okay. Excuse me. What is going on? How come the last element ends up going all the way off the edge? That doesn't seem to make sense. It does make sense that we would have a count of 1 for each element. That's fine. But why would we end up going so far off? 0 to 1 for the first element, 1 to 2 for the second, 2 to 3 for the third, and 3 to 4 for the fourth. Excuse me. The last value that is so confusing. What should these numbers be? First off, in this case, let's try that. Excuse me. Well, yeah, I mean, once the fourth element is set, all of the last elements, all of the d plus 1 values are going to be just set to n, to 4. So that should be so. But yes, you should see that 4 is in there potentially. But yeah, you see 0, 1, 1, 2, 2, 3, and then 4 is at the end. But how come the bounds are wrong though? Like that should come after the things that we don't see anymore, right? It should be, this is 1, 3, 6, and 9. 9 would be set to 3 at this point. We shouldn't actually have, 9 should be set to 4. What are these counts? Actually, we'll do it this way. Okay. Let's see this. Let's see how this goes. Okay. So 0, okay, so we see 1, 1, 1, 1. Yeah, all right. How come position of I equals the current? Oh, that's why. Oh, I see the problem. I see the issue. That's subtle. That's subtle, but yeah, I keep using that word. You're overusing that word. I see the problem. That's not something I would have realized. It's kind of annoying. I see the issue. Okay, so these are set as expected. No, the problem is down here. Because this recalculation over here, because we incremented D when we swapped, right? Increment this position. Now, if you position of D is incremented at some point, now if you try to take array of D again, you'll end up, I guess what happens is once you place 9 where it's supposed to be, if you try that's really confusing. Actually, I don't know. What happened? Wait, what's wrong? How did position D end up at 4? Wait, what? What? I think I know what happened, but Hard to tell. Hmm. Do we sprint D? Okay. So we have D of 3, D of 3, D of 6. Oh, D of 1 is 4. Oh. Oh, that's interesting. What? They all got placed. Oh. This D doesn't change. I'm so confused. I'm so confused. So this D down here. Oh no, we do have to. We do change it. What is going on? I'm just utterly confused. When you swap, you want to increment what you swapped from. You swap array of I into position D. When you swap again, you want to add 1 to where you're putting into that bucket. Yeah, that should be fine, right? That should be okay. These are the starting point. Position of D is the starting point of that particular bucket. You shouldn't be swapping into buckets that are full. Like that's kind of what's happening, is that we're swapping into buckets that are full. Somehow. I don't know how that's happening. I don't know, I'm so confused. That's why I'm really confused. So the exact point that it fails is when we have 9, 9. At the bottom here we have 9, 9, but we have position 4 earlier too, I think, right? Oh, this is really confusing. 4. This is right at the end. So the previous thing was X was 9, D was 9, div was 1, position of 9 was 4. So how did, what was I? I was still 1, I think, must be. Well, maybe that's why. Maybe I'm not supposed to be comparing I against this here. I was 1. Yes, I figured. So we get to here and start swapping things around. Excuse me. So I is 1. Position of D is way beyond 1. So 1 is not in the right position, or this, yeah, whatever's here. 9 got swapped here. It's not in the right spot. So yeah, it's not in the right spot. We want to so this part is true, this part is false. So this is so we'll try to move 9 to the correct position, which should have been 3. I don't know how we got position D is 4. When and where did that happen? When D is 9, where do we get D is 9 anywhere? Oh, here we go. Oh, this is looping a lot, huh? Uh-oh, maybe that's why. Did we get into an infinite loop? Is that what it is? Is that we're just getting an infinite loop of swaps? That's not supposed to happen. Whoa, no. Once this is in the correct spot, it's supposed to move on. What? Oh, I think I see the problem. This doesn't loop correctly when you fill it. I see the issue. Oh, I see the problem. Once you've filled the oh, that's why. Yeah, it's looping infinitely and then running into problems. So once you add all the numbers that have a 1 into the first 1 bucket, and you're still looking at things in the 1 bucket, you can't tell that you're in the 1 bucket because the next position in the 1 bucket is to your right, and so you're always going to be not greater than equal to or equal to that position. Oh, I didn't think about that. That's awkward. I see. So we actually want to have another set of bounds, we'll call them, and then we have positions to put in those bounds. Oh, that's so awkward. Okay, so there's a little more information we need to do this properly. Got it. We don't actually want to change those bounds on this array, on this while loop. All right. Well, when you learn about you could make the bounds the same as the position. That's okay. It could be the same thing. Probably one of the few times where you could say, and the bounds are actually going to be constants. One of the few times where you can use this operator, and so you perform the bounds checks. So this actually bounds. And then you also update the positions. Something like this ought to work. Compiler error. Default initialization of object of const type. Alright, so I guess you can't do that. Guess you cannot do that. Still a runtime error. Signed integer overflow cannot be represented by int type int times 10. Oh, right. That's subtle too. I didn't think about that. So, not subtle. That's another minor thing. So dividing is fine, but multiplying is a little bit more complicated because of the overflow. Yeah, performing this multiplication. Yeah, you just don't perform this at the end if it's too big. So you would say, I mean, you could do this. Like, there's a few ways to handle this. Just have an if statement and say total total should drop to 1. If it's greater than 1, then we multiply. Once total is 1 though, then we don't multiply again. Something like that, I don't know. Is that right? When total is 1, we don't multiply again. Wow, this was really challenging. I have to say this kind of, I mean, I haven't implemented Radix Sort too many times, so I guess that's one reason. But the problem is that you do right. So when total is 1, total is greater than or equal to 1. No. Yeah, when total is 1, you don't multiply again because total is about to be decremented and you're about to exit the loop. Yeah. Okay. That's a little confusing, but yeah, so we can get rid of all this debug code, I think. Let's try our test cases first and then see. I had a few test cases I was looking at before. Okay, it's a lot of code. It's a lot of code, the debug statements, but if these are correct, that's probably right. Oh, wrong. Brother. Excuse me. Which one is wrong? Oh no. The bottom, not the bottom one, but the second to bottom. Okay, this one. So is my algorithm incorrect after all? I would be upset. I would be upset. I'd be frustrated. Yeah, I think this sort's not as stable as I'd like it to be. I think that might be the problem. I don't think it's a stable sort. I think that's the issue. Hmm. 71 expected 61. Interesting. Let's print the sorted array at the end here. I already know the answer, but that's okay. I actually don't know if I can write this for loop here. I think I can't do this over a normal array. Okay, let's try it. Oh, it compiles. Oh, I wasn't expecting that. So 0, 39, 2, 5, 6, 7, 29, 100. Okay, that was that is not what I was expecting from my Radix sort. It's pretty close, but not quite right. Why? How do we end up with 39 over here? Maybe I should just print this after each step. Oh, not that one, but this one. After each iteration, print and see what happens with our. This is probably like the slowest implementation of a Radix sort ever. It's like we're over an hour now. 0, 6, 100, 2, 5, 7, 39, 29. Okay, we could probably comment out some of the other debug statements now. Yeah, I think it's just not stable. Some of the assumptions that I'd made about what would work here, I think are not correct. Just a wall of the debug code here. Okay, now we can get rid of these two. Don't need these anymore. Okay, how are we doing? Hour and 18 minutes, all right. So 0, 6, 100, 2, 5, 7, 39, 29. That's before the first pass. After the first pass, 0, 1, 2, 5, 6, 7. So the least significant digits, right? Next we have, so we sorted by the second, which in this case was 0. These are all 0, 2, 9, 3, 9. Okay, that's fine. Now we sort by the next, which basically these will be put in random position. So actually, if this was stable, if these were placed in the right spots, then this wouldn't have happened. So this is not a stable sort the way that I'm doing this. You can make it stable by, you can recursively sort the each bucket themselves. So if I sorted by, so I was wrong what I said before. Like this approach is incorrect. If it was stable, it'd be fine, but it's not a stable sort the way that I'm doing this. This part particularly is not stable. What you would do to make it stable is you would basically collect into each bucket from left to right instead of performing these while loops. I guess that would be like your quote-unquote pigeonhole sort rather than a accounting sort. Or yeah, because what I'm trying to do this in place. Well, I think you can do accounting sort in place, or a Radix sort in place. As far as I know, you can. You can do it stably and you can do it in place, but I seem not to be doing that correctly. The reason why this isn't working in place is why. I think because the counting sort gives you your frequency. We could use a pigeonhole sort. I think a better thing to do would be the problem. Problem that we run into is we would end up overwriting data. That's part of the issue. So you can't just swap things out. Now what is interesting though is if we go from left to right, and if we go left to right and we sort each bucket based on the most significant digit. So in other words, we sort the leftmost digits, sort everything, and then in each of those buckets that we've now created, we can then quote unquote recursively sort. The problem with that though is that while it works, don't know if we can do that iteratively. That would be kind of challenging to do iteratively. What that would become is like, that becomes, yeah, I don't know if we can do that iteratively. It's a little bit less efficient if it's not iterative. Yeah, you could sort the contents of each bucket recursively. The problem there is that it's because you end up with if you try to do it iteratively, you have sort of like a trying to iteratively search through a perform an iterative depth first search over a tree that's not a binary tree. A depth first search over a tree, like an in-order traversal of a tree that is a binary tree, is not too difficult, but a tree that's got an arbitrary number of children per node is a little more challenging, to say the least. Can be done, but as I said, it's almost not worth doing it. Better off just recursively doing this. But the reason why I don't want to do that is I thought you could do this the other way around. Well, if the reason why you can't do it the other way around is because it's not going to be stable anymore. And the reason it's not stable is like we saw, you can't do it in place, or you might be able to do it in place and stable, but I don't know how, because the things that you're going to put into the bucket, you have to overwrite what's there, and you have to do something with that data. I mean, you could like copy that section of data and then copy, and then write what you're supposed to write in there, but what's the point of that? And then not only what's the point of that, but then how do you reference that back to, like if you use indices, you're supposed to copy these indices to those to this set of spots. The problem is then the other indices that refer to those spots would have to be remapped. Let me think about that for a minute. That's kind of what I did, is I just swapped the indices. Yeah, you lose track. You lose your other references to those indices, get kind of messed up. Um, you could actually, but then that's pretty awkward. Yeah, actually this ends up being, that just ends up being copying the array using, yeah, that's not in place. Yeah, you could do this in place if you do it recursively, I think so. Yeah, you just need to sort from left to right and do that. Yeah, that's fine. All right, let's do that. That's fine. That's okay. We'll do it recursively. No big deal. We'll sort the bucket. Sort the bucket contents. Sort the bucket contents internally. So we're going to say, trying to avoid doing this recursively, but what are you gonna do? What are you gonna do? All right. So we have a few things. So we're gonna say there's an array, int array, reference. I think you could do this, C++. And this is not a copy of the array, this is a reference to the array. I think actually arrays are pointers, so you can just int array, which is a little bit weird to write it that way, but I think you can. And then we're going to say, actually I don't know, can we do this? Well, we'll figure out a way to get that in there. It's not like a vector, where a vector you'd have a reference to the vector. Can we do 10 reference? I don't know if that works. It's like int, I don't know. Can we do this? I don't know. Maybe. Who knows? It's actually, what are the other? We'll come back to that in a minute. What we want is have an array. We have a range, I. And these are consts. If we could type. So we have a range that we're going to operate on. We also have a divisor we're going to use. And then we have a reference to an array. It's not a UB2, it's an int. We're going to sort this part of we're going to radix sort this part of the, or portion of the array. And we're also going to use, we're going to do these things recursively. So the way we're going to do this is for each int I equals a, we have a reference to ns, I is less than or equal to b, increment I. We are going to do pretty much the same algorithm that we did down here. Very similar thing. So pretty much copy paste that. So count. First we make a count. Then, okay. Have this. divided by divisor modulo 10, array of I, increment the count. We have positions, we have bounds, current 0, we update our positions and bounds accordingly. That's all the same, although this is a, it's 0 to 10. We say for I equals A less than or equals, A less than or equal to B. We're going to perform the same routine that we had over here, where we swap things where they ought to be. And then, excuse me, from here, we can call on each bucket recursively. And then recursively sort each bucket. So now for each, now the problem with this is I think also you end up with kind of a lot of extra memory, because you're gonna recreate this memory each recursion. So I think you actually end up with W squared memory. Yeah, because you create this array for each recursive routine that you call. Yeah, see, that's the thing that's awkward about this. Like, it's not quite right. You end up with the size of the word squared memory. Doing it this way, actually implementing it this way. There might be a way to implement this as better. Like, this is probably not the most efficient or effective way to implement this. Yeah, this would be if you recursively used bucket sort or Radix sort, which would be counting sort. Now again, we could go back to what this is if I insist that I want this to be stable, or rather if I want to do this in a way that's not stable, I guess. If I want to have it in place, you could do it in a way that's stable where it's in place, or it's not in place. There is a way to do this that's stable in place, stable and in place Radix sort. I think there's a way to do that. Can we do that? Let me look that up. I'm pretty sure there's a way to do this that's better. And I'm just not doing it the right way. We're looking for Radix sort. Excuse me. I'm pretty sure. So this is like some much needed practice on Radix sorting, but definitely. Forward recursive most significant digit and then least significant digit. Yeah, they use dynamic memory allocation, right? Well, I don't know. The thing that's awkward about this is the problem with this is the problem that we just ran into while trying to do this is how do you do this in place when you want to move your elements in the buckets? Now you figured out which elements go into which bucket, or you figured out how many elements go into each bucket, but how do you actually, like, you can use a copy of the memory and put everything in the right spots in that memory and that copy and then swap the arrays, you know. That's fine, you could do that, but that's not in place anymore, right? Would be stable but not in place. How do we do this in place and stable? And then again, yeah, forward recursive is how I would do it typically. And W, LSD variance can achieve a lower bound W for W of average key length. Splitting over variable length keys into groups as discussed above. Optimized Radix sorts can be very fast. We're going to domain that suits them. Less graphical data, many practical implications. That's not a limitation. Large keys implement can hinder things. Induced number of passes becomes the bottleneck. Yeah. If you have very large keys, you can have issues where the logarithmic factor is better when you're dealing with. If you're dealing with very large keys, you might hit a point where you're better off using a normal comparison sort. In-place MSD Radix sort implementation. Okay, so binary MSD, binary quicksort. Oh, is that what that is? Implemented in place by splitting the input array into two bins, the zeros bin and the ones bin. The zeros bin is grown from the beginning of the array, whereas the ones bin is grown from the end. From the end of the array, the zeros bin boundary is placed before the first array element. The ones bin boundary is placed after the last array element. The most significant bit of the first array element is examined if this is 1 swapped with the element in front of the ones bin boundary. Okay, it's grown by 1, 0, and 0 is grown until the zeros bin and the ones bin reach each other. The zeros bin and the ones bin are then sorted recursively based on the next bit of each array element. Recursive processing continues until the least significant bit has been used for sorting. Oh, so the problem with this, though, is how much memory do you use at each step? Because if you're recursively sorting the two bins, the issue that you run into is the stack frame on top has to have data to figure out where the beginning and the end of the two bins are. Which in this case is just 2 integers. But that means that each recursive step you have 2 more integers on your stack frame. And the word length, I guess that is actually not constant memory, but memory proportional to the word length, because it's just 2 bits, not 2 bits, but 2 integers times the word length. Okay, that's fair. In my case, oh no, we're okay. I'm sorry. No, I'm not. I'm wrong about this. Actually, we're fine. It's the radix times the word length is how much memory. I'm sorry. It's not the word. It's not the word squared. We're fine. We're okay. We're fine. I was wrong. I was like thinking about it. Like how did we end up with using so much memory here? It just seems squared in this case because the number of digits is also both 9 in both cases, but we're fine. Okay, no, we're okay. That's, I guess, they call that binary quicksort. I guess you can call it binary quicksort. That's interesting. Radix, also binary Radix sort. That's fun. Anyway, okay, we do this recursively. We're fine. Okay, position bounds I0, perform our swaps, and then recursively sort each bucket. So for I equals 0, I is less than 10, plus I, we're going to radix, or F rather, of a few things. A, B, div, array. So we're going to calculate A and B and div an array. Now we're going to go from most significant bits down. So we're going to use most significant bits now recursively. Excuse me. So A and B are going to be the Also, this is if A and B is greater than, excuse me, so we can do this. X is going to be, it's going to be the bounds of I, and Y is going to be bounds of I plus 1. Yeah. It's confusing here. That's just Y. I is greater than or equal to 1. We can set bounds I minus 1 or 0. So this is inclusive though, so it's actually going to be this bound minus 1 and the previous bound is actually the beginning point of this array. That's correct. Yes. So that gives us X and Y. And we also say if Y minus X plus 1 is greater than or equal to 1, I don't want to get too used to using the LeetCode editor. I use all kinds of different editors depending on the context, so I don't want to get too comfortable with the different features that it has. Yeah, so if I is greater than or equal to 1, then we can use the previous bounds. If it's 0, obviously we'll return 0. Bounds of I minus 1 is the right side, and then as long as we have at least one element in our bucket to look at, then we'll recurse. We also want to make sure and div is greater than or equal to 1. That's the other part. Yeah. So the bucket could be empty. The bucket is empty, then we're not gonna touch it in that case. Okay. So yeah, so something like this. Radix of f radix array, and we'll go 0 to n minus 1. Div, we'll say power of 10 to the 9th, and array and radix. And then we can pretty much dump this. We're not going to use this. Okay. How about this? Yeah. Okay. How about this? What does that do? What? It's a redefinition of I? Is it? I don't think so. Huh? Oh. Ah, I see. Writing too many awk loops. I don't even write that many, but that comes from writing awk loops. Deduce return type can't be used. Sure. Division by 0. Okay, interesting. Oh, it's going to be greater than or equal to 10. Yeah. I think that's the mistake. Are we getting this again? This error, this issue? What's happening? What is happening? What is going on? Okay, let's see. Count is 0. I equals 0. I equals A. I equals less than or equal to B. Get X. This array. Divide. Modulo 10. Yes. Increment that count. Position bound. Set this to current. Increment. Oh, I don't need that anymore, do we? That's redundant. Okay. Array of I. Oh, you know what could be the problem? This array could be arbitrary. Ah, I think that's the problem. That's probably the issue, that this is just like a random array of memory that doesn't have anything in it. It also could be like recursing infinitely, I guess. Oh, it is a pointer. Okay. Huh. That's interesting. Okay. Do 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 do. Hmm. Oh, it's sorted. But why do we get an overflow? By the way, this is not what I was expecting for how this would be sorted. What? Why did all of these? What happened here? What is going on? Do 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 do. Da na 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 na. So confused. So confused. Zero 6 29 257 39 100. Oh, I know what happened. I see the problem. So, okay, the first however many we had here, 1 2 3 4 5 6 7 8 of these were meaningless, and then suddenly we put 100 to the end, and we put 29 and 39 to the end, and then we sorted the rest of this. And I don't know where these came from. I think these were actually sorting the buckets themselves. So each of these buckets were then sorted recursively. So you had 1, 2. So how does this work? This bucket was then sorted recursively as one whole bucket, which was then sorted into 0, 1, 2, and 3, which really there was just 3 buckets, 1, 2, and 3, and that's why you have 1, 2, and 3. I think that's what's going on there. That's a little confusing as to what's happening there, but so it gets completely sorted before we run into any issues. So where the last printout seems to be where the problems start. Why would that happen? Each of these buckets, I guess when you start one of these buckets, so what happens is you 0, 2, 5, 6, 7. You could have like a base case here. I guess that's the issue. I kind of don't have a base case. That's sort of the problem. As long as div is greater than or equal to 10. And then after that, oh, I see. I got it. Yeah, it doesn't really matter then if we put the base case over here at the top. Then we really don't need this. Which is where it should be, actually. That's actually the problem. It's just the base case in the wrong spot. Almost always have the base case at the top, by the way. So if this is less than 1, or div is less than 1, and return. Excuse me. So Oh, and that's not X and Y, it's B and A. Well, in this case, it would be B and A. So there's got to be at least one element. Div's got to be greater than 1, and the other things we don't care about. Okay, what? Why? Why? I don't get it, man. I don't get it. I don't get it. How is there an overflow? Another way of saying this is if B is less than A. Oh, I see. That's probably why. I think the reason is I think it's got to print go into an infinite loop. No. There we go. Yeah, I see the problem. I think what happened is I thought it was reasonable to have sorting an array of one element, but that doesn't make sense. And I think that was the problem, is that you can't sort an array of one element, because if you do that and you try to split it into 10 elements here, like 10 buckets, you run into problems. And I think that was the issue. Running into issues here somehow. Trying to sort one element, and recursively then sorting one element over and over again. Yeah. Although those shouldn't. I don't know why those run into issues. I don't think that was supposed to have problems. I don't know why. Because I think if the problem was that we were, oh, that's why. Yeah. Because then this would be, well, this would be false, right? This div would divide this by 10 each time. But the problem is that when div is 1 and the element is 1, I think you run into issues. I don't know. It's confusing. Why? It shouldn't actually matter. I don't know why. What? Why would this run into problems exactly? I think I misunderstand something. Really, a runtime error. Stack buffer overflow. Huh. Why though? Count is so let's say if you have A is equal to B, right? And div is 10, or div is 1. A is equal to B, div is 1. Let me come back to this in a moment. Let's do this. Oh. What? What is going on? Runtime error. Okay. Is it if we have a 0? Is that the problem? Is it just if I have a recursive call? No. Seems like if I have a difference between the element sizes, something like that. Huh. I think this part of the code is written incorrectly. I think it's this. I think it just so happens to work correctly in some of the other cases, but this, it's not this base case. The base case should be fine. That actually, I was okay with that. This routine is not correct. It's not correct. I don't think you need to divide by 10 anymore, by the way, or take modulo 10 anymore. Oh no. Yeah, that's the least significant. We're trying to take the most significant digit. Yeah, so yeah, that's probably why. Oh no, I'm sorry. No, I had that right. I'm so confused. We divide and take modulo 10. Yeah. Yes. Because if we have a no, that's right. I did have that right. That's how we get that particular digit. But what is causing this runtime error? It's got to be something here. These loops, man. These loops cause issues. All right. Oh, okay. Almost certain that this is being called. This is the culprit. 5060. Yeah. So we get stuck somewhere in this loop. It's frustrating. Oh, I see. Our bounds are no longer. Oh, I see the problem. Our bounds are no longer dependent on the range of between I and B, A and B. That's the issue. That's why. Current starts off at 0. And yeah, it's a good thing we checked because I thought something was weird here. Oh, okay. That's better. That's kind of a subtle thing, but I really didn't want to try to figure out why. Try to figure out what was wrong. I think that's all we need. So we're we spent a lot of time on this, but this was good to like review how to write a Radix sort. Okay. Can remove the debug statements. And again, this bottom one we could probably use the STL for. I think we can use accumulate. So something like this. So standard accumulate of but I don't know if we could do that quite exactly the way we'd want to. This makes it kind of complicated because you're referencing the array in 2 spots. You may be able to use a pointer and then decrement the pointer, but I'm not sure if it's worthwhile to go into all that. Excuse me. I don't know, maybe it is. Let's try it. Maybe it is, let's try it. All right, so it's gonna be standard array or begin of array plus 1, standard end of array, if I could type. I'm gonna start off with 0, or start off with 1 rather. And we're gonna apply this lambda expression. It looks like the following. We're gonna take our const. Now the problem with this is we're going to dereference our pointer rather than take the pointer itself, which is awkward. Yeah, let's take a look at that. Let's look at the algorithm library in the STL. See if any of these will suit our purposes here. We don't want to move or fill the transform. Destination range. It's not really what we want to do. Range of elements. It's more like accumulate or fold is what we're looking to do. Let's just do this for now. Oh. Okay. Can't see. This is what happens when you can't see the keyboard. You just mash things. Let's also. Can we generate random numbers in Python? How do we do that? And that probably, oh, typed it correctly, okay. Random pi, we have a seed, rand bytes, rand range, start stop, randomize from the range. Oh, that's interesting. Choice doesn't build a range object. Oh, we want choice range, okay. We don't need, oh I see, rand range, rand int, alias for a rand range b plus 1. So we want rand range and we want to choose some subset. Yeah. Let's have some permutations. I cannot read that at all. use 4x in it permutations of we're going to use rand range of 0 to 10 to the 9th plus 1, and we're going to select x for x in, we're going to perform, we're going to take this range, and we want a certain number of these. Here we go. We're going to do rand range of x. Rand range x in range. We want 5 numbers. Yes, imagine that. So we're going to generate 5 random numbers and all those permutations. How about that? How about that? There we go. Hey. Okay. So this is really useful for something like what we're working on here, or just messing with our test cases in general. What's interesting is the numbers that we picked. Oh wow, it's wrong. The numbers that we picked. What do you mean it's wrong? It's wrong? What do you mean it's wrong? It's wrong. It's wrong? Oh, I can't believe it's wrong. Ah! Excuse me? Oh no. And it's wrong? Oh, you gotta be kidding me. By the way, we just tested like 120 use cases here. Alright, we need to get back our, hold on. Actually, no, we can go back, it's fine. Need our debug code. Brother. This is the one we need to copy. And go back to whatever we had. Okay. And it's wrong. And it's wrong. Of course it's wrong. Why is it wrong? What? Oh man, you gotta be kidding me. Why is 564 in front of 496? How did that happen? How did that happen? What? They're all wrong. Every case is wrong. Brother, Buddha, Buddha. You've got to be kidding me. How did that happen? How did that happen? What do you mean it's wrong? What do you mean it's wrong? Excuse me? Excuse me? Brother. What? How did that happen? That's bewildering. Excuse me? How? Huh? Huh? Ooh, excuse me. I don't know, man. Yeah. Do 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 do. Ba na 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 na. Ba na 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 na. It's obvious I did something wrong. Obviously, I did something wrong here. Rum bum 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 ba da da dum bum ba dum bum 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 bum. This reminds me a lot of we can close this. That reminds. Oh, okay. I guess not. Don't have the. Okay. Oh, dude, I can't believe it. I bet the STL has a Radix Sort best built in too, which just makes this even more like comical, I guess. All right, we gotta debug this. The debuggery, the absolute debuggery of this. Alrighty, let's keep going. Oh, we had this issue before. Need this loop or a loop like it. Do 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 do. Oh boy, that's Susie, huh? Susie. So, okay, first off, we have 81457, 81457. Okay, we have 81457 for a while here, huh? Whoa, how many iterations does this go through? It seems like too many. Whoa. What is going on with this algorithm? This seems really excessive. What? All right, maybe it's just wrong if they're not. We try to process one at a time. Oh. Okay. Wow. That's really confusing. seems like if you try to process one element, you can run into issues. I don't really know why that would be the case, but apparently my code doesn't handle single elements nicely. And also it looks like it goes through 1, 2, 3, 4, 5, 6, 7, 8. Can't just. All right, we're not gonna try to count it that way anymore. That's just it's fine. Put it into another editor. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Went through 22 recursive calls before. Huh. That's kind of a lot, huh? I think the reason is because. Oh yeah, well, we printed everything before the base case was reached, so yeah, there's a lot of calls, a lot of calls that just stop dead in their tracks. I don't know, man. Some cases they're equal to each other, and so when we try to process that, yeah, I guess the issue is that we try to do this processing, and this should handle one just fine. We try to do this processing and it just kind of doesn't work properly. It's really weird to me, I don't know. Basically all the positions will be 0, except for like some of them are going to be 1, some of them are going to be 0, some of the bounds will be 1, some of the other bounds will be 0. And I is only one value, D is that value, if it's in the right spot, which it has to be, right? Because these bounds were set this way. It'll just exit here, and then it won't continue here because I guess it'll try to call these other routines. That's a lot of extra calls actually, because it'll call until this div goes all the way down, and it's actually going to call for each. Oh, that might be the problem. It's going to call for each bucket. You could still probably run into issues with this though. Like it's going to try to call this on each bucket, but all of the buckets are in the same spot. So right. Oh, that's actually the problem. Nope. We're fine. Actually, I had the right idea initially. It's not 0 anymore. It's A again. These are. I think it's fair to say these are subtle bugs. That's actually the problem. It's not the base case. Still not the base case. There might be another spot where yeah, there we go. Okay, that's got it. Now I think it's better if we do this because that ends up generating kind of a lot of extra calls if we don't nip that in the bud here. So yeah, all right. Let's go with a few of these, huh? Let's take another one. Another very large set of numbers here. Okay. How about a set of random numbers? See why Python's so nice? See why it's such a, it's just, there's so much you could do. It's so flexible. It's whatever your needs happen to be. I think that's really why people use Python so much, is that it's just because it's so flexible. You don't need, like, whatever your needs are, you can just mold whatever your Python script you have to those needs, like, very quickly, very quickly and very, like, on the fly. Specifically for this, like, I was thinking about writing a whole C++ program to, like, generate all kinds of test cases, but actually whatever specific test cases you need, you could just write a small Python script to do that, and just do that every time. And you don't actually need, like, you don't need a larger program that will do that, generate test cases as you need them. Like, you could just write a script to do that each time, and it's not that much faster or efficient, because the other program that you would write, you'd have to configure it for that particular use case anyway, and you might have to just extend that program for that use case, something like that. I don't know, but yeah, Python's pretty great. So what we want to do is actually have, we're not going to use permutations now. Now we're just going to say, let's take X in some random range. So we're going to say like 100 numbers, 100 times we'll do this. And we're going to say for some Y in, I can actually do it this way, print Y for Y in, or rand range, we'll do it that way. Rand range of 0 to billion for X in range, and this could also be a random number. I think they said it's like 30,000 or 20,000. I don't know, we'll do 10,000 to the fourth or to the fifth. We'll do 100,000. Yeah. So this is going to generate 100 of test cases that we might want. 10 to the fifth, yeah, 100,000. Okay. There could be one, oh, we need to slightly modify that. So 100 test cases, and we could do like 200 test cases actually. Well, that might be too many. We don't need range from 1 to that number. Oh no, I'm sorry. Yeah. From 1, and this also is going to be from 1 to this number. Did I do that correctly? So we're going to, 100 times, we're going to get a random number from 1 to 100,000, and then we're going to pick take a range from that 1 to 100,000. So we're going to do this 100 times, and then each of those 100,000, 1 to 100,000, we're going to create a number and have a, yeah, I think that's what we want. Oh no, close that. Oh. Not quite what we want. Oh wow, it's taking some time, huh? Okay. Oh boy, it's going. Okay. We are testing this code. Big time. There we go. Okay. Oh boy, that's a doozy. Yeah, 100,000 numbers. 100,000 numbers that are in the range of between 1 and a billion 100 times. Okay. Maybe we should have just done it like 5 or 6 times instead of 100 times. Oh, that's probably excessive. All right, we can close Notepad. Notepad's not made for that. Yeah, we'll just close it. It's okay. It's okay. Oh, that's fun. Put it at like 10. 10. Still a lot, but oh wait. All right. You know it's bad when you're writing to a text file and it takes an eternity to open, or even not just open, but just to write it to the text file in the first place. You know you've got a lot of data. Wow, this has picked some pretty big numbers, huh? Okay. Whoa. Can we get the whole thing in the buffer? Is that gonna work? Is that gonna cut it? You know what I think? I don't know if it's gonna work here. We could try it. It's probably this passes, then it's probably correct. Yeah, I think my own tests would be like more difficult potentially than the tests on this website. Not always, but some cases. It's going. It's going. It's cruising. It's fun. Uh-huh. Oh no! Oh, it's wrong. You gotta be kidding me. Serious? It's still wrong? Oh, I'm so sad. I cannot. You're kidding. You're kidding. What happened? What happened, man? Also, I didn't realize I had all this print code here. Oh, man. So if I submitted it, I would have failed. I'll try again. I'm wondering if the debug had any issue, caused any issues. I don't think so. Disappointment. Disappointed. How did we fail this? Come on. Really? Really? Okay, all the other test cases are fine except for this one. This one is just too much. Pending, it says. Okay. Judging. Alright, here we go. Now, how did we get this wrong is the question. They're all wrong. Every one of them. How big are these test cases? Can we open this? Alright. Well. Let's take the first one. Because everything's wrong except the first one, right? Let's do this. Let's actually generate just one. Let's do it this way. Oh no. Oh. Alrighty. Alright. So we're wrong. Somehow we're wrong. It's a good thing we're heavily testing here. Why is it so wrong? Okay. So far away, so far away, for far too long. I need to check the correctness of. It looks like it sorted it correctly. Yeah. Ha. What? Do we just have like one number that's just in the wrong place? Is that what's going on here? Oh, okay. I don't know. We have to programmatically verify that the sort worked. Okay. Check. And it's going to be equal to and equals array of I is less than or equal to array of I plus 1. If check. Failed. Really, if that ever happens. Unless this piece of code is wrong, and then I'll be really sad. I don't think so, but that would be kind of awful. Here I am saying this problem is so easy, and it's wrong. Brother, you gotta be kidding me. How did that happen? Oh boy, that's great. Well, that's why you test things. Brother, how did that happen? Why? Why is it wrong? That's the question. I have no idea. I couldn't tell you. Whatever it is, it's not obvious to me. Well, okay. What did I do? My question is, here's the problem. Here's like makes things even worse, right? You ready for this? So I could take the first 32 elements or whatever of this array and try to sort it, and so that way I have a smaller test case to work with, so I can actually like try to think about what's happening here, try to process this. Obviously, I'm not going to be able to work through a test case by hand that has 100,000 elements. It's just not, that's not feasible. What is really funny though is like, if I were to extract the parts of this, try to figure out the parts of this, like where it failed, because it's a recursive bucket sort where you're breaking it up into 10 buckets and then recursively sorting, it's very likely that that I won't be able to figure out. I won't be able to figure out what went wrong. Basically, if I try to extract the broken part, it'll do a different routine on that. Not a different routine, but it'll approach it slightly differently, and it won't necessarily give me the same problem. All we know is that it's wrong. The logic is wrong. Something in there, some assumption in here is wrong. A, B, div, array, F, array of I. What's interesting here is that this gives you a pointer to the array, so we don't need to, we could just, we could actually process it this way. But the problem is position bounds, current starts at A. So we start our position of I at current, and we add each of these counts. These counts we determine by dividing modulo 10. Yeah. so dark out. Feels like it got dark like an hour or two ago. And it's only 7 or 8 o'clock. It's pretty... Yeah, it's only 7 o'clock right now where I am. I have to say the in-place sort is really challenging. Trying to sort this in place has been extremely challenging so far. Actually, this is wrong. Really? Yep. Oh no, it's fine. No, we're okay. Bounds of 0. Bounds of 1. No, we're fine. We're okay. Oh, these are wrong. Yeah, it's actually the other way around. That's what's wrong. That's what's wrong. Duh. I do this. I make so many mistakes, man. Sometimes it's hard. I don't know. I don't know how to like. How do you write code in a way that doesn't have errors like this? You know, like it's really just a matter of like paying attention to what you're doing. Here I am saying this is so easy. Yeah, because the way that I define these bounds were actually, these are starting points, not bounds. So I should have named this bounds. I should have named this as like start. That's more appropriate. And then, because bounds kind of imply it's to the right. And the, yeah, I think that's why. So basically, not basically, if y is okay. So If I is less than 9, then we're going to pick the x will be the starting point of I, and y is going to be the next starting point minus y. If I is all the way at the end, then we still pick the starting point of, if we're looking at the last section, last bucket, then actually, now what's interesting is it's not, so that's an interesting one. The last value would be b, so I did this wrong. Yeah, okay. So you would either be, right, first, headset is letting me know that I've gone on long enough, gone on for far too long. So now you're gonna hear a buzzing, another buzzing noise. You have 2 buzzing noises now, occasionally 3. So if it's the last bucket, then still a starting point, same starting point. However, there is no other starting point beyond that bucket. So you just take the ending of the array as the last spot. I think that's the error. It's very likely the problem. And all the other test cases that worked correctly were just randomly happen to work correctly. Oh boy. This is an easy question. It's just if you don't program it correctly and you mix yourself up. You mix yourself up by mixing up the positions and starting points and trying to do it. Well, doing it in place is fine, but yeah, all the different positions and starting. But there's just a lot of pieces to this. I think I don't really know. I don't really have an excuse other than like, yeah, there's a range, and you have to pay attention to your range and setting up each piece correctly and reference the other pieces you set up. I don't really know what to say other than like, yeah, in theory it's relatively simple, but in practice, actually coding this is like, there's definitely a lot of pitfalls, I guess. There's definitely a lot of places you could trip up. And by the way, we are not done yet. We are not done yet. So now we're going to do 10 of these. Okay. We copy pasted it into the bookmarks bar. That wasn't what I meant to do. Also, I spoke too soon. I don't actually know if this is totally correct yet. Pretty sure it is, but there could be some other detail that I missed. Very likely that's something I missed. Looking at it like this. Don't want to know if it's wrong. Don't want to know that it's wrong. There we go. All right, I think we got it. I think we finally got it. Yeah, okay. Interesting. So these are kind of slow, actually. 600 milliseconds for. Oh, is that because? Yeah, it's because it's recursive. It's so fast. It's iterative. It's so fast when I said iterative. Oh, man. By the way, we can also just return when it's equal. That might speed things up a bit. It's like 100 times faster if it's iterative. Alright, let's go for it. Let's do it. Let us do it. Is it wrong? Oh, it's right. Okay. Hey. Hey. We use less memory, but that wasn't even optimal memory. This is this was an interesting question. Yeah, the theory was pretty easy. Coding it was really challenging, it seems. Ah, man, I kind of want to use an iterative approach, because you could just copy the array each time. Now, what we could do is we could do this in place, and we have much better memory, I think. But one detail is, yeah, this would be a lot faster. So if we did this iteratively, it's like 100 times faster if we do it iteratively. And that would consist of, that would actually copy the array each time at each iteration, which is fine, but just copy and swap the array multiple times. I think we should have done that. That would have been better. I'm also wondering now if the iterative approach that I used was incorrect, not because it's not in place, but because it was just wrong. That's possible. That is definitely possible. I don't think it was wrong. I don't think it was wrong. I mean, it was wrong, but I mean, I don't think it was wrong. The iterative portion. Sorry. I think it was wrong, but I don't think it was wrong for the reasons. I think I actually just got this part wrong. I think otherwise it would have been okay. How about we go back to what we had originally and see if I can do this iteratively in place. Let's see if that's a possibility. So let's do this. Let's copy this. We're gonna go way back. Way back. Hours ago. Going back hours in time here. Give it a moment or two. Part of the issue is, and we can copy paste the solution that we just moved or tried to move. Oh, we TLE'd on this. Whoa. Whoa. Wasn't expecting that. And this whole thing could just be Okay. Interesting. I was not expecting that, not at all. Oh, it's probably because this is this debug. I forgot about this. Or some other debug messages going on here. Yeah, that'll definitely TLE. That'll definitely cause a TLE. Really, we should just have a check for whether this is in the correct position. I don't think it will be. So maybe I did have it wrong the first time. I thought maybe I just set this up incorrectly. There was some bug. That's not the case. Actually, there is a bug. Yeah. Whoa. Really don't need to print this, but a few things to say. So we should copy the array each time. We're going to do that in a moment, but specifically, yeah, this is not a stable sort unless we copy the indices correctly. I think if we do that, though, it'll be a lot more efficient. Yeah, this just isn't correct, I think. It is this routine. That's the problem. So we could do like previous array, and then we can say instead of counting, we can use can do a vector position bounds. Don't really need that anymore. We can just say like which. And I don't know if we should use a stack. I don't really need a stack. It's more like a queue. You really don't even need a queue. I mean, you could just use a vector. It's fine. I don't think we need limits or unordered sets. in either of these solutions. So we can say an array of vectors, of integers, and these are going to be indices. Really, we don't need any of this stuff. We can just say, don't even need a count. X, D, say which D dot pushback I, and then we don't need this anymore. We can then say this we do need to actually initialize though. Yeah, I don't like that we're going to be initializing all these vectors over and over again. Maybe it's better if we do this. Just do this once. Let's use stacks instead of vectors. I think that's better. Yeah, it's better. It's definitely better. Because we'll clear the stacks each time. Instead of popping from the back and making it confusing. And then what we're going to say is I think these should be queues. Yes. Also a confusing thing. Okay, push into the queue. And then we're going to say excuse me. I'm going to say array of I is equal to we're actually going to do it this way. For I equals 0, x equals 0, x less than 10, increment x. We're going to say for or while which of x dot empty I'm going to say array of I increment I is equal to which of x dot front auto reference current queue CQ pop, and we're going to say previous of I, and then that should cover everything. Yeah, that should be fine. That should be fine. So we say which queue we push I as the index, and we're going to set array of I to the previous of that, and then we're going to update the previous array, or this previous array is going to be equal to array of I, and array of I goes to 0. And if the total is greater than 1, that's just to prevent the overflow. Something like this, and then finally we would return previous. You actually don't need to overwrite in between here. Oh, we will. In other words, write 0 there. You don't actually need to write 0. I should also use a smaller test case here for this. Should definitely use a smaller test case. Judging, okay, yeah, it's taking a while because these test cases are enormous. Also, this was not quick at all. This was not quick at all. Oops. Oh. In fact, I think the first iteration I had was faster. It might be because we're using the queues. Okay, let's see. So this is wrong. That's interesting. I wasn't expecting that. Which one is wrong? 64 and 61, 94 and 61, okay. That would be this one. And interesting that the others were correct. Oh, whoa, whoa, whoa. Oh. Oh, it's full screen mode. Which I do not care for. How do I exit full screen mode? There we go. Okay. How are we doing on time? 3 hours and 17 minutes? Okay, I mean, we already solved it, but we want this to be quick. This to be quick, I want this to be correct. Huh. Oh. That's why. Why the other ones were correct, I don't... Why would the other ones be correct? That's weird. I don't know why I should have done that. I was singing a song about God, and this was more about me, not about God. This moment, I was like, huzzah! We did it! Oh, invalid test case. Oh, I see. Was that the problem? Blank is not a valid integer. Fair enough. Fair enough. Hopefully this is a little bit faster. Oh man, my computer's gonna crash. Computer's gonna just shut down. Uh-oh. Uh-oh, computer don't die. It's doing like 3 things at once. It's trying to run OBS, trying to run Notepad, trying to run the online judge. Oh yeah, are we okay? Hey, alright, that's kind of slow. It's kind of slow. It's actually not as fast as expecting it to be. Alright, I think we go for it. I think if it passes those test cases, it probably is fine. Oh, my foot! Oh! Oh. It's actually slower. Oh, he uses more memory and it's slower. Bruda. Bruda. Brother. You're serious? Are you serious? Is you serious? Yes. True. Oh wow. That's awkward. You know, I don't know how we could do this more efficiently, quite frankly. Excuse me. It's not much faster. I don't know. Run this routine 10 times. It is a lot easier to code, that's for sure. But I don't know how fast you can go. Oh, that's a lot. That's whoa. Yeah, it's kind of random how quick it's gonna be. Yeah. It's interesting that the recursive solution was faster, or seemed to be faster. wasn't expecting that. Well, this is a solution that, excuse me, is relatively quick. It's not that quick, but it's relatively quick in the sense that you don't need to really think too hard. It's quick to code, maybe that's the way to express it. I don't know, man. It's kind of interesting, actually. I think the n-log-n solution would be faster. Just a simple. So I think the way to do this really quick is not to use Radix Sort at all, but to use like binary sort or binary heap sort, I think they call it. Something like that, binary sort. Or binary quick sort, that's what they call it, yeah. Yeah, that'll be the fastest way, I think. This is So actually, I was thinking just running a simple n-log-n standard sort would be pretty quick, but I guess it's not. Yeah, my sorting routine's slow. It's slow. You really don't need these because we're going to write the array here. The array actually is only just like, it's kind of just temporary. Trying to think of a faster way to do this. Yeah, I think just a different algorithm would be faster. It's kind of challenging to get a. There's like a lot of different ways you can set up your heap sort and your counting sort and your rather not your heap sort, a lot of different ways you can set up your bucket sort or your distribution sort, however you want to call it. Let's just say distribution sort. Yeah, there's a lot of different ways you can set up your distribution sort. Ultimately, a lot of different ways you could set up your distribution sort. Ultimately, we probably could use a faster sorting algorithm, but we're going to leave it at this. I thought this was going to be pretty quick, but I was wrong. Yeah, trying to get it to be in place and stable is challenging. It's not necessarily in place and stable. But yeah, pretty interesting either which way. But yeah, I guess a binary quicksort would have been the best idea. I suppose, but we didn't do that. So yeah, all right. Thank you for watching. I'm gonna stop it there. I don't know. I'm not gonna go mad trying to figure out how to make this the fastest it could be. I think it's a little bit much. But definitely a really interesting problem. Optimizing is an interesting endeavor as well. I'm not going to go into all that though. It's just a little bit excessive, I think, for now. I've already spent hours trying to get my code to work correctly. Yeah, I wasn't able to get an in-place and stable Radix sort using counting sort. I don't think you can, because counting sort I don't think is intended to be in place. I think you can do, maybe you can do like pigeonhole sort, For the counting sort, that's kind of what I just did now, though. That's actually what that was. Pigeonhole is one that I just coded. That's a lot easier to think about. A lot easier is pigeonhole sort. I'm wondering. Yeah, pigeonhole sort's a lot easier. That's what I just did, but that's not in place. Maybe I could have used an in-place algorithm, like a standard in-place sorting algorithm, and I could have used references to the, or I could have used pointers, right? I could have sorted the pointers using a standard sorting algorithm. And I'm trying to think how that would work. Maybe there was a standard stable sort algorithm that I could use. I don't think that works either. No, that doesn't work either. That doesn't work either. Yeah, the problem with that is I don't know, man. I don't know what you could do, because I could sort, quote unquote, sort the buckets themselves, but the problem with that is that you need to sort of put everything into the buckets. Like, it's all well and good that you sort the buckets themselves, but like each bucket, you need to know what's in that bucket. And I guess, yeah, you could use a standard sort for the buckets. Like I said, I use the counting sort's fine when you have only 10 numbers to work with. Really, any sort is fine. But again, adding each element to the bucket is the tricky part, because how do you... It's not even adding to the bucket that's hard, it's that if you don't want to copy the entire array every time, like pigeonhole is great for what we just did, but the issue becomes then how do you write your results back to the array, right? Let's see. Is there an in-place distribution sort? I'm curious about that. In-place and stable distribution sort. Bit sort, I think. Oh, blit sort. Okay. Octasort, likely the fastest. Quad sort, blit sort. A2 sorting in place in linear time. CLRS. Oh. Walk CCC, not me. Forget what the CLRS is. It's good though. kind of want to read. Go visit this website. Oh, it is CLRS solutions. Okay. Right. An algorithm for sorting might possess some subset of the following three characteristics: linear, stable, in place, using no more than a constant amount of storage space, in addition to the original array. Okay, that's what we want. We want all three of those. Does such an algorithm exist? Is the question. I remember reading this I bought the Kindle for CLRS, and I remember reading this chapter 1 and 2, 1 and 3, 2 and 3. As the sorting method used in line 2 of Radix Sort, so that Radix Sort sorts n records, b-bit keys, and O of bn time. Explain how or why not. Oh, that's interesting. So we really only want, well, yeah, we want all three of these, I think, for our Radix Sort. N records have keys in the range 1 to k. Show how to modify counting sorts that it sorts the records in O of n plus k. You may use O of k storage outside the input array so your algorithm is stable. How would you do for k equals 3? A is counting sort, gives you linear and stable, but it uses extra memory, right? That was the problem. I was trying to do it without using that extra memory. 2, quicksort partition is the quicksort partition. 1, 3 is linear, not stable, but it's in place. Yeah, quicksort, right? True. And then, alright, and actually 2 and 3 stable, but not linear and in place. I mean, I guess you could say, like, I don't know, insertion sort or something. What's stable? Bubble sort, maybe? I forgot what stable means exactly. Stable means, like, if two duplicate elements, you take multiple duplicate elements, if there was some order that they were in from left to right, then that you have the same order in your sorted list as you do in the original list. I think that's the way to describe it. I want to say insertion sort is stable. Yeah, I think so. Bubble sort's probably also stable too. Oh yeah, there you go. Insertion sort, they said. Okay, D. Yes, no, no. So A is yes. You can use counting sort, but you have to use extra memory. But the other two would be, you wouldn't get insertion sort, you won't get O of bn time, and then quick sort, you actually can't get O of bn also for insertion sort or quick sort, because quick sort's not linear. Quick sort, both of those are not linear. So yeah, even though quicksort is, oh, I'm sorry, quicksort is, oh, I'm sorry, my mistake. That's not really true though. Quicksort is like expected linear, not actually linear. Not worst case linear, 1 and 3. So B is no. That's interesting. No explanation for why B is no, and then modify counting sort so that it sorts the records in place in O of nk plus k time. You may use O of k storage outside the input array. Is your algorithm stable? How would you do it for k equals 3? Interesting solution. In place, but not stable. Yeah, I was going to say, I don't think it's stable if it's in place. It can't be stable if it's in place. You can do counting sort in place. Yeah, yeah. Actually, the algorithm that I had was stable, not stable, in place, but not stable. So we couldn't use it for the Radix Sort. Huh. So this is kind of what I was thinking about when I was looking at this. Like there's like a lot to consider here, actually. Getting this to be really fast, then I think it's fine to use two arrays, but you're probably better off using binary quick quote-unquote binary quicksort rather than what we used here. Use multiple. Yeah, I think actually the binary quicksort can be. Is it stable though? I think the binary quicksort would have kind of the same algorithm here. I think you could do it in a way that's still stable. I'm thinking about it because yeah, you can keep all of your zeros that you move to the right spot. Maybe you just need to count how many ones or zeros you have, how big this split is. No, you do run into problems. Yeah, you can't do it in place and keep it stable. The reason why you can't, even with a binary sort, is because binary partition is problem why the reason why it's still not stable is because of as soon as you swap a 0 with a 1, that 1 is now out of order of the other ones. If there's any 1s before it, then it's out of order. Yeah, you kind of need to like bubble all of your 0s and 1s in order to keep it stable. No, you can't do it that way. So I think you're just stuck with a similar algorithm to what I had, where you copy the array each time. Or you can do this recursively. Really can't do this. If you're going to do it recursively, it's a little bit faster, I think, because you don't do the copying and you're stable. But what you're doing is you're not you're sort of recursively sorting the contents, which is fine. But the problem with that is it's recursive, which is like 100 is like really slow. Like if you could find a way to do that iteratively. I mean, you could traverse so you can actually do this very efficiently, but I think what you'd have to do is perform like an iterative traversal, like the way you would traverse like a binary tree. Instead of a binary tree, though, it's like a tree with multiple children. Tree with an arbitrary number of children. That's challenging, and you'd have to traverse your problem space in that way. I guess you'd have to create nodes too, like you have to create a tree for the problem. I think it's still going to be kind of slow, even though even though you're doing this iteratively, you have to like create a tree. I think it's better just to do it recursively and call it a day. I don't know how everyone got 100% though on that, or how people got really fast numbers. Probably maybe you could do like I said, maybe there's just like faster ways to implement this. But it looks like actually the iterative approach where you copy the array is not the fastest, which I thought was interesting. Maybe I think the recursive approach is slightly faster. But all right, I'm gonna go. Thank you for watching. I will talk to you soon. Have a good rest of your evening, your day. Yeah, it's gonna bug me that I didn't get the fastest speed because I don't know. I don't actually know what the fastest would be. It's got to be some super fast sorting algorithm. Actually, you know what they may have done? The folks who get the fastest speed may have just used a really fast sorting algorithm. Just a standard sort, just faster in all the test cases. Done. All right, I'm gonna go. Thank you again for watching. Talk to you soon. I was gonna do another problem. I thought that was gonna take me like 10-20 minutes, but as it turns out, with hard problems on LeetCode, it could be really hard. Could be really challenging. So I did some exploring and thinking about like different algorithms that we could use, and got a little bit of a review on sorting, so that's good. But yeah, this is interesting. All right, I'm gonna go. Take care. Talk to you soon.